I apologize about the break in the video. There shouldn't have been a break. However, my computer started to die and I didn't have it plugged in. Had to run and go get the charger. But now that we've gone through Fermat's theorem, what I want to talk to you guys about is some care needs to be used when thinking about Fermat's theorem. And to show you what I mean, let's look at these two examples. F of x equals x cubed. Let me draw you the graph of this. Look, something like this. Now, Fermat's theorem says if f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c must be equal to 0. Now, let me go ahead and take the derivative of this. F prime of x is equal to 3x squared, just a simple power rule. Now, is there such a place, is there a c value such that the derivative equals 0? Well, yeah. 3x squared, or sorry, 3c squared is equal to 0. And if you were to solve this, you'd find c must be equal to 0. So we did find a number that satisfies the conclusion of Fermat's theorem. However, just because the conclusion of Fermat's theorem is true, that doesn't mean the conditions are true. This theorem only works one direction. If you have a local min or max and your derivative exists at c, then f prime of c equals 0. F prime equals 0 does not mean that there's a local min or max anywhere. This function does not have a local min or max anywhere. The derivative exists everywhere, so the first condition is true. So at c, the derivative exists. But, sorry, I said the first condition. The second condition is true. The derivative exists at c. The first condition is not satisfied because we do not have a min or a max. Let's look at another one. F of x equals the absolute value of x. I'm going to draw you the graph again. Looks something like that. This definitely has a local minimum. The local minimum is right here at 0. So in this case, local min c is equal to 0. I guess we could say at c is equal to 0. However, the second condition is not satisfied. The derivative does not exist at 0. Okay, so now we cannot guarantee the conclusion. F prime of c, so f prime of 0 must be equal to 0. Okay, we really need the second condition in order to guarantee the derivative at that c value being 0. So again, just because you have a local min or a local max does not necessarily mean the derivative must be equal to 0 at that point. Okay. So now we got a new definition. Critical numbers. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. So what that is telling us is to find a critical number, what we need to do is find the c values where f prime of c equals 0, or the c values where the derivative does not exist. Okay? So now, with this definition, we can just rephrase Fermat's theorem in a better way. If f has a local minimum or maximum at c, then c is a critical number of f. Okay? So what this is telling us is that if we want to find local mins or maxes, what we should do is look in the places where the derivative is equal to 0 or where the derivative does not exist. That's exactly what it's telling us. So it gives us a procedure to find minimums and maximums, and that's going to come in handy for the closed interval method. But first, let's do two examples. Find the critical numbers of the function. So here's our first function, f of x equals 4 plus 1/3 x minus 1/2 x squared. So if we want to find the critical numbers, it gave us a procedure to do so. Take the derivative, set it equal to 0, and solve. Also take the derivative and see, does it not exist anywhere? So taking the derivative of this, derivative of a constant is 0, derivative of 1/3 x is 1/3, derivative of negative 1/2 x squared is negative x. So taking the derivative, finding the c values, f prime of c is equal to 0. All that means is 1/3 minus c is equal to 0. If we add c, we get 1/3 is equal to c. So here is one of our critical numbers. In fact, this is our only critical number. Here's why it's our only critical number. The derivative, if you look at it, it's a linear function. Linear functions have a domain of negative infinity to positive infinity. So this derivative is defined everywhere. It exists everywhere. So we're not going to get any critical numbers from finding the c values where it doesn't exist because it exists everywhere. Therefore, this is our only critical number. We have a critical number at c, or sorry, at 1/3. Let's do another example. F of x equals x to the 4/5 power times x minus 4 squared. So, first thing, let's go ahead and take the derivative. F prime of x is equal to, we're going to use a product rule, derivative of the first function, so it's a power rule, 4/5 x minus 1 from the power, you get a negative 1/5, times the second function, minus 4 squared, plus the first function, x to the 4/5, times the derivative of the second function. Now, this is going to be a chain rule. We've got a function inside a power function, so we do the derivative of the outside function first, bring the 2, bring it out front, times by 2. Now, we drop one power, x minus 4, and then we got to multiply it by the derivative of the inside. But the derivative of this inside is just 1. Okay? So it makes it a little easier on us. We don't need to multiply by anything over here. Okay, so now what I'm going to do is I'm going to simplify this a little bit. 4x minus 4 squared divided by 5. This has a negative exponent, so I'm going to put it down at the bottom. X to the 1/5 plus x to the 4/5. Bring the 2 out front. X minus 4. Okay, so I've got a fraction right here, right there. Or, well, this is not a fraction. We can put it over 1 though. Make it a fraction. I'm going to combine the fractions. That means I need to find a least common denominator. This is the only denominator. I mean, we've got 1 there. So that means this must be the least common denominator. I'm going to erase up top here. So we got f prime of x is equal to, it's going to be all over this least common denominator. Now, since this term over here already has the least common denominator, this numerator stays exactly the same. However, this numerator, or this fraction over here, does not have any of the denominator, any of the least common denominator, so I'm going to multiply it by the pieces it doesn't have. So I'm going to multiply it by this piece right here. So I still got plus 2x to the 4/5 times x minus 4, but now I'm going to multiply by this, 5x to the 1/5 power. So I'm going to get rid of this. Now, look, this has an x minus 4, this has an x minus 4. I'm going to factor an x minus 4 out. It has an x minus 4 squared. So, taking it out, x minus 4. Not only that, I'll wait on that part. So, let's see what we have left over. We've got a 4 times, this was a squared, so I took one out. So, it's going to be an x minus 4. Plus 2 times 5 is 10. X to the 4/5 times x to the 1/5. If you remember your exponent rules, we're going to be adding the exponents together. 4/5 plus 1/5 is 5/5, or just 1. All divided by 5x to the 1/5. Now, if you were to look in here, you're going to see we've got a 4x minus 16 plus 10x. We could fully simplify this now to an x minus 4 times a 4x plus 10x is 14x minus 16, all divided by 5x to the 1/5 power. So here's our final fully simplified derivative. I told you earlier on we're going to be needing to simplify the derivatives for this purpose right here. So now what we want to do is we want to find f prime of c such that the derivative is equal to 0. So I'm going to plug in c everywhere and set this equal to 0. So c minus 4 times 14c minus 16, all divided by 5c to the 1/5 power. That must be equal to 0. Alright, well, the only way that this fraction could be 0 is if the numerator is 0. So we could completely ignore the denominator. So c minus 4 times 14c minus 16 is equal to 0. And now we just set each piece equal to 0 and solve. This one you could easily see c is equal to 4. This one, 14c minus 16 is equal to 0. If you were to add over the 16 and divide by 14 and simplify, you're going to get c is equal to 8/7. Okay, I know I did that really quickly. So, here's so far our critical numbers. We've got c is equal to 4 and c is equal to 8/7. There is another critical number. All we did was find where the derivative was equal to 0. Here's our derivative again. Equals x minus 4 times 14x minus 16, all divided by 5x to the 1/5 power. If you recall that We also have critical numbers where the derivative doesn't exist. The derivative doesn't exist at 0. I can't plug 0 into here, otherwise I would be dividing by 0. So, c is equal to 0. That's our last critical number. F prime of 0 does not exist.